Welcome back. We've been talking about fallacies, how they're flaws in our reasoning, and how they might lead us to draw improper conclusions in our personal lives, in our economic lives, in our financial lives. And today what we're going to do is explore some statistical fallacies and some causal ones. So what we have here is just a list of the fallacies we're going to be talking about in this mini lecture video. So to get to the conjunction fallacy, let's consider this Linda problem. Which is Linda is 31 years old, single and outspoken. She's very bright. She majored in philosophy. And when she was a student, she was deeply concerned with issues of discrimination, privilege, and also participated in anti-nuclear demonstrations. This is some information we're given, and now it's our job to rank the following statements according to their probabilities. Linda is active in the social justice movement. Linda is a bank teller. And Linda is a bank teller and active in the social justice movement. Now, who thinks A is the most likely? Who thinks B is the most likely? And who thinks C is the most likely? And when you ask this to large groups of people, a lot of people say that C is more likely than B. But that's impossible because C, that Linda is both a bank teller and active in the social justice movement, is comprised of both A and B. It's impossible for this event, C, to be more likely than one of the things that comprises it. Necessarily, this conjoined probability, this conjunction, has to be at least equal to, less than or equal to the probability of one of its events. This is known as the conjunction fallacy. And this conjunction fallacy, because we're not engaging that critical part of our brain, is also committed by PhD students in statistics and students who have had this rule explained to them. So let's take that complex thing that we just learned and give an example. Suppose we have a random student selected from this class. Which is more likely? That they've also taken Core 160, that they're an equestrian, or that they're an equestrian who has also taken Core 160. So now that we've broken it down into terms that we're more familiar with, we can see that it's impossible to be more likely to be an equestrian who's taken Core 160 than to be either an equestrian or someone who's taken Core 160. Our next fallacy is the base rate fallacy. And to consider the base rate fallacy, let's consider the disease problem. And this might be a little too on the nose for right now, but suppose we have a test for disease that is 90% accurate and someone tests positive. What is the chance of me having the disease? Take a minute and think about what you think the chances are. And the answer is it depends. First of all, what does it mean to be 90% accurate? Well, when I hear 90% accurate, I hear that 90% of all people are correctly classified. So how many people actually have the disease? It depends on what we mean by accurate, but also depends on how prevalent the disease is in the population overall. So suppose we have this 90% accurate test for a disease that affects 1% of the population. That means 10 people out of 1,000 have this disease. This is the base rate. So if we test all 1,000 people in this population, 90% of the 10 who have the disease test positive, but also 10% of the other people, the other 990 people, 99 people who don't have the disease test positive. So in this example, 108 people test positive for a disease, but also only 9 of them actually have it. So your chance of having the disease when you test positive is 9 out of 108, or less than 9%. Probability is hard, and it's important for us to recognize this when we're dealing with probabilistic arguments. Finally, let's talk about post hoc ergo propter hoc, which is our causal fallacy. So for those of you who don't know, this means after this, therefore because of this. After the thing, therefore because of the thing. And this is a causal fallacy, a fallacy of cause and effect, whereas our other fallacies that we learned this lecture were statistical fallacies. This one has to do with cause and effect. And what it says is, if event A happens immediately before event B, event A caused event B. But actually what it's saying is this is not the case. So why is this a flaw in our reasoning? Why is it fallacious to say that because event A happens immediately before, it is fallacious that A caused B? Well, let's consider this line graph on the right. It shows that as downloads of the internet browser Firefox went up, so did membership in Wicca. Therefore, downloads of Firefox increase membership in Wicca. Let's see an example of this. This is clearly fallacious. Maybe what's going on here is some unobserved component, like people become more aware of Wicca with wider dispersion of the internet, and with wider dispersion of the internet, more people are also downloading the browser Firefox. In other words, it's not the Firefox download that's causing it, it's some unobserved event. Let's see some examples of this, which is, I had been doing really poorly this season, then someone gave me neon laces for my cleats, and I won 3 races. Those laces must be good luck. If I keep wearing the neon laces, then I have to win. Now, it's not true that getting the laces caused you to win 3 races. But because this person won races after receiving them, this person concluded that they are good luck, and this is a fallacy. Let's see with our favorite play in the Crucible. Last night, I tried and I could not say my prayers, and then when someone walks out of the room, suddenly I can pray again. This is an example of a post hoc fallacy because the fact that Giles' wife was reading her book has nothing to do with the fact that he couldn't say his prayers. A more plausible explanation might be that he forgot. It even says in the Crucible that sometimes he forgets. And with that, let's close out this mini video. We'll come back in the next one with some fallacies of irrelevance.